Hello everyone, I'm Umaimah Mitsalia from Biomedical Engineering at Universitas Airlangga. Before we begin, I would like to extend my deepest gratitude to the reviewers and editor who have played an essential role in refining this research. Now, I would like to present the research on wheelchair safety system using physiologic control to avoid obstruction. I became part of this research with Mr. Endro Yulianto and Mr. Triwiyanto. In this presentation, will be divided into 4 points. One is introduction. After that, we talk about the material and method, and then the result. And last, we will talk about the conclusion. First, the introduction. Ease of mobility is one of the needs that can improve people's quality of life. Disabled people rely heavily on walkers to improve their performance. Wheelchairs are one of the mobility for people with disabilities. A wheelchair for people with disabilities are also made in such a way that they can comfortably move independently without the help of others. The wheelchair can be controlled by using voice control and then joystick control or using electromyography or EMG signal. It takes safety feature on wheelchairs such as obstacle detection to maintain a safe distance for obstacles. Good safety control in wheelchair is difficult to achieve if you only rely on biological signal control. In research in 2012, the distance set is 1 meter, but the average wheelchair stopped at a distance of 400 centimeters from an obstacle. It happens because of the inertia force. It's necessary to regulate the motor speed when the sensor detects an obstacle. In DevNet's research in 2018, the speed of the wheelchair with PWM or pulse wheel modulation is regulated. Android, the change in motor speed is more linear and comfortable for the user. But the motor speed selection made directly by the user via Android make it wheelchair insensitive. And then in Sankardo's research in 2019 compared the speed control between PID and fuzzy, it is found that PID still produce a fairly large overshoot when there is a change in speed, either accelerated or slowed down. This research aimed to design an adaptive safety system for a wheelchair by resolving these issues. To address the speed regulation issue using physiologic control system, which regulate the motor speed based on pulse width modulation. This is what the sensor placement position looks like. We use 4 ultrasound sensor, each placed on the front, left, right, and back. U1 for the sensor on the front, and U2 for the sensor on the right, and U3 for the sensor on the left, and U4 for the sensor on the back. And we use 2 motor on the left and the right. And then this is the ultrasound sensor that we use. This is LV Maxonar EZ1. The sensor provides very short to long range detection and range. And then the sensor detects object from 6 inches to 254 inches or around 6 meters with a resolution of 1 inch. And the sensor has 33 degrees transmit beam width. This is the diagram block of the system. The input block obtained from logic command. There are 4 commands: forward, back, turn left, and turn right. And the input is also from the ultrasound sensor. Then we process in Arduino Nano, where in the process block, there is input processing using fuzzy logic control. When an obstacle is detected by ultrasonic sensors, it will be converted into a PWM value through fuzzy logic control process and continue through the DC motor driver left and right. We use fuzzy logic controller to control the wheelchair. Physiologic has a degree of membership between 0 and 1, as opposed to classical Boolean logic, which only has 0 and 1 value. Fuzzy logic process include falsification, rule-based inference, and falsification. These methods make system more flexible and adaptive, allowing for better handling of uncertainty and impression in complex contexts. Falsification is process of turning input value to fuzzy value, and then the rule base contain the decision-making. Each rule has two major components: an antecedent block between if and then, and a consequent block after then. Inference determines the fuzzy judgment made throughout the rule-based process, which result in a fuzzy collection of decisions. Logical operators such and or not specify how fuzzy variables are joined. The fuzzification is the reverse of the fuzzification process in convert the fuzzy output into crisp value to the applied to the system. And then in this study, we use the Takagi Sugeno Kang method approach, which is simpler to implement in programming language due to its singleton set on the output variable. We defined our system in two modes, free area and corridor area. And then in corridor area, also include two modes, following right wall and then following the left wall. The left figure shows the physiologic mechanism when the wheelchair is in a free area. The wheelchair will be on free mode when the front sensor or back sensor read the distance more than 50 centimeters. And then there is a forward command or backward command. In this mode, PWM for the motor will follow the value of the fuzzy process, while in the corridor area are shown in the center figure and right figure. The center figures show the following left wall, and then the right figures show the following right wall. So in the corridor area, use the error value obtained from the difference between the distance read and the set distance or safe distance. In this mode, PWM for the motor will be different and left and right. PWM value will be reduced or added by the value of fuzzy logic. The experiment was carried out at three different distances consisting of a distance of 10 meters, 3 meters, 1.8 meters, and 1 meter. In the corridor area with a wall following system using a corridor with a flat wall that has a width of 2 meters and a length of 6 meters, with 3 experiments in each mode to find out the result of the distance between the wheelchair to the wall. And then the result is when the wheelchair approaches an obstacle, it first detects the barrier at a distance of 2 meters. This happens both when moving forward and moving backward. Initially, as the distance dropped from 2 meters to 70 centimeters, the PWM decreases significantly by 9%. After that, there is a sharp decline. When moving forward, the PWM reduction is 4.3%. And when moving backward, it is 4.7%. The decrease in PWM causes the motor to lose strength, preventing the wheelchair from moving efficiently. This method allows the wheelchair to adjust speed based on the distance to obstacle and enhancing user safety. For distance over 2 meters, the wheelchair moves quickly but gradually slow down as it gets closer to the obstruction. On average, when moving forward, the wheelchair stops at the distance of 34.06 centimeters from the obstacle. When the moving backward, it stops at an average distance of 45.16 centimeters. In this figure shows that both studies begin with the wheelchair at the distance of 40 centimeters from the wall. So once detected, both wheelchair move away to maintain this distance from the wall. The sensor adjusts the wheelchair's position to keep a conscious gap from the wall. In right following mode, the wheelchair maintains a distance from the right wall between 28 and 68 centimeters, with some data spike possibly caused by interference from the other sensor. In the left following mode, the distance from the left wall ranges between 28 and 56 centimeters. The motor PWM settings were adjusted to help the wheelchair move in a straight line. However, that the wheelchair's movement remained something winding with distance from the wall varying between 28 and 68. And this is the result of sensor reading area. The experiment was carried out by providing an obstacle in the form of a brick that has width of 5 centimeter and a flat surface. The sensor can reach it up to an angle of around 30 degrees at an optimal distance of 100 centimeters. Sensor response is also influenced by the shape and the surface area of the readable hitch. One ultrasonic sensor can read obstacle up to an angle of around 30 degrees. The sensor response is also influenced by the shape and surface area of the readable hitch. Wheelchair can reduce speed linearly when there is an obstruction with the fuzzy process by changing the linguistic input from the distance reading to a PWM to be output on the motor. Wheelchairs can run a safety riding system when walking in free areas and corridor area. To acquire the best result, it's vital to determine the precise location of the sensor and consider the movement of the wheels to avoid altering sensor reading when the wheelchair is moving. Excessive use of multisensory system needs to be minimized to prevent sensor data loss, which can affect the fuzzy process. The research results can be implemented as a safety system solution for wheelchair for tetraplegic sufferers to help support their daily lives. That's all for me. Thank you.